Hi, my name is Courtney Boyd, and I'm going to present on genetic algorithm-based technology optimization for digital twin robots. I was on my high school's robotics team, and I've been interested in robotics for a long time, so I hope this project will be interesting to you as well. So we're going to start off with a little bit of background about digital twins and genetic algorithms, and then we're going to get, which is going to be sections 1 and 2, and then sections 3, 4, and 5 are going to get a little bit more into the meat and potatoes of the paper that I read, followed by a discussion where I'll talk about the references that I read and how they're relevant to this paper, and as well as I'll talk a little bit about my research that I'm doing in Dr. Chin's lab, and then we'll do a conclusion. So, what is a digital twin? A digital twin is when you have one physical asset in the real world. So, you can touch it, feel it, uh, work with it with your hands. It doesn't have to be a robot. In this presentation, it is going to be a robot, but I've seen applications of digital twin where the physical asset was a plane. I've seen a mining site, I've even seen a digital twin for a hotel. And then, so for a digital twin, there's the physical asset, also followed by the digital twin, right? So you have some sort of model, a CAD model, some sort of virtual twin, and the virtual twin and the physical twin are able to exchange data. And this digital twin technology is useful for a lot of different applications. For example, in manufacturing, you may have a robotic arm that does some task, and you might want to have a digital twin that does the same task so you can speed it up and then see what kind of wear and tear, what can you expect for, regular use. When will you have to replace this object? Or even if your physical asset is something that's very expensive and you want to try a new task automation, but you don't want to risk damaging your physical asset, you can use your digital twin to do the new task and make sure that no damage is caused to the digital twin. And then when you recreate that same thing with the physical asset, you know that the likelihood that it'll be safe is pretty high. The digital twin technology is also useful for remote collaboration. So you can have the physical asset in like China while you have the digital twin in Germany, right? So you're able to collaborate even internationally. So what is a genetic algorithm? Before we get into genetic algorithms, we can start off with something that's a little bit more well known, something that more people are familiar with. What is survival of the fittest? A lot of us learn about Darwin's theory of evolution in probably elementary school, 5th grade, 4th grade. The way that I think of survival of the fittest, I always think of the bird example where there's two birds in a forest and the forest has a lot of nuts in it. One bird's beak is hard and able to crack open these nuts. The other bird's beak is incapable of opening these nuts. Which bird's offspring are more likely to survive, right? And the bird that has the beak that's able to open these nuts is more likely to survive and have, offspring and be successful because it has a lot of food available to it. Whereas the bird that cannot open the nuts is less likely to have offspring. The offspring are less likely to be successful because they can't eat the nuts. Their food source is limited because they're physically limited, right? So they're not fit enough to survive in this nutty forest. And that's survival of the fittest. So how can computers imitate evolution? How can a computer understand this sort of survival of the fittest technique and implement it, right? So there's a couple of major components, right? So the first component being a population of solutions. In this paper, we're going to talk about paths, right? Path planning. So maybe you want to get from point A to point B. So a population of solutions, maybe one solution is you go up and across, or another solution is you take the diagonal, right? You take a diagonal path, or maybe you go in a zigzag. And so those three solutions, we have three solutions right there, and that would be our population of solutions, right? Then you want to do a fitness test for a path. Maybe your fitness test can be the shortest distance between uh, point A and point B. So the shorter the distance, the more fit that solution would be. And then you want to have a mutation, right? So if between point A and point B, if all of the paths in our population just go up and across, up and across, up and across, there we can't get any good information out of this. We can't find the best solution because we only got three options. So we have to introduce some mutation. So instead of it going up and across, we need a way to make, okay, this next solution is going to be diagonal. This next solution is going to be zigzag. We have to introduce some sort of change in between the paths. And then once we have these changes, we have to update the population. So now I've said go through the diagonal, make sure that this is in our set of solutions that we can pick from. So let's do a definition. A genetic algorithm is a random search strategy that provides a shortcut to the best solutions. That's the way I think about it. If you don't take anything else from this slide, I think that definition is a pretty good one to take. So that's why I read it directly. So now into the meat and potatoes of the paper that I read. So in genetic algorithm-based trajectory optimization for digital twin robots, their virtual twin, which you can see in the bottom left corner of the image on the screen, was created with Unity. Unity is a pretty popular game engine for 2D, 3D, virtual reality, mobile app development. And then their physical twin, as you can see on the bottom right hand of the screen, and I even put some of the microcontrollers that are used. There's also gyroscopes and sensors used for this for the physical robot. So genetic algorithm based path planning. We need to know what is the desired task, right? We have to create this path. So as you can see in this top right image is in the Unity engine, right? This is in Unity. This is the virtual twin. So this whole environment is the virtual environment. The robot that you can see on the left is going to take the goods that it's holding, the white boxes. It's going to go through the two cylindrical objects, and then it's going to place those two objects inside of the white stacking area that is on the right. So you have your start position, you go in between the cylindrical objects, you drop them inside of the stacking area. Bam. And of course the robot has restraints. Even the restraints in the virtual realm have to match the restraints that the robot would have in the real world, right? So they've accounted for things like, physics, weight, and things like that inside of speed. The speed of the robot would also be a restraint. Those sort of things are accounted for inside of the Unity game engine very easily, which is nice, which is why people like to use it. So how can we describe the task, which is getting our goods to the stacking area? How do we describe the task with numbers? So what we have to create is this raster map that you can see in the bottom right of the screen, right? So these numbers on the outside of the map are your regular Cartesian coordinate plane, right? where this first box would be considered, 1, 1, and so on. We're all, familiar with the Cartesian plane. But these numbers inside of the box will correspond to n inside of our equations that we'll see on the next slide. And the rest of these numbers are representing spaces that the robot can walk in, right? Safe areas, if you will. But you see that the box labeled 31 and the box labeled 17, they're both blacked out. Why are they blacked out? Because those are where the obstacles are. 31 and 17 are where the cylindrical objects are. So the robot has to pass through box 24, right? So in this raster map, our starting position is box 45, and it needs to go through 24, which is in between the cylindrical objects, and then our good stacking area is this box number 3. And there are some parameters in the bottom left of the screen right here that tell you a little bit about the Unity environment that they created for this project. All right, so here are the equations. Remember, from the raster map that we just looked at, those numbers that I said would be in the next equations, you see it here. So our x and y from these equations are used to create the paths for the robot to go through. And the paths, each path is a member of our population. So a path would, that's what we're interested in, getting the best path, right? So x and y, we use those to create our steps to create the path. Then we need a fitness value, right? So now we have our population. How do we check our population? We get this fitness value, where this is going to be our distance in the Cartesian plane, right? And so we know distance from like physics 1, where it's, the difference between 2x values squared plus the distance between 2y values squared, and then you take the square root of that whole quantity, right? And so then you want to take the probability for each path, where, the higher the fitness, the higher the probability of this path being selected, right? And then so you want to do that. So you want to get the fitness for each path, and then you want to get the probability of this path occurring. And, right, so fitness calculation, and judge, is it good? And then preserve the best individual, preserve the best path. Obstacle collision detection, of course, that is happening by this mu. The mu is going to be 0 if the object is colliding with one of the cylindrical objects, right? So that automatically makes your fitness low. So then it's less likely. It has a low fitness, it's less probable, right? And then gene mutation, right? We have to do different paths, form a new generation of populations, and then do it all again until everything works out. And I have some of the parameters here for the algorithm, like population size being 50, all of that here to the right. So the first thing we need to know is, does it work? When the robot says, okay, I have this path, does the physical robot even follow the virtual robot's path off the jump? That's the first thing you need to know. And it does. You can see that very clearly in this image in the top right of the screen, where you can very clearly see inside of the Unity engine, the robot is to the right of these cylindrical objects, and then in the lower one, you can see that the robot is in between the cylindrical objects, both in the virtual world and in the physical world, so that data communication is doing well. And you can see we get that communication in real time using the Unity engine right here. You would see it in the left of the screen, right? So yes, the physical robot is moving with the virtual robot. So, okay, it works, but how do we see we identify trajectory deviations? How do we know when it's not working so well, right? So center 1 is going to be the bottom of the goods, and center 2 is going to be our stacking area, where we want to get the goods to, right? So the distance between where the goods end up and where the goods should end up is going to give us an indication that our trajectory has deviated, right? And what causes this? Physical error, like gyroscope angling or measurement error. If you measured the distance between the cylindrical objects to be this distance, but you're off by a centimeter, that's going to cause error, right? So you can see in this graph in the upper right hand corner that as the number of tests, so as you have the robot try to go through this path, the more tests you do, the smaller the distance between where the goods end up and where they should end up gets. So the path is being optimized, and that's a good thing. So discussion, how could this study be extended? So this was in an XY plane, but my first question was, what happens if I introduce a Z-plane? What happens if I want my good stacking area to be on a shelf or something, right? How is that considered? How would that be considered with this genetic algorithm path planning? I found this interesting resource, Digital Twin Robotic System with Continuous Learning for Grasp Detection in Variable Scenes, which sort of goes at this Z-plane question. And then there was another question, which was the poles are in the same place, they only create one virtual environment. What happens if you test the paths? What happens if I move the poles or if I move the stacking area? And so this other paper, Optimal Path Planning and Execution for Mobile Robots Using Genetic Algorithm and Adaptive Fuzzy Logic Control, is they use a little bit of image processing so that you're able to change the path up and then use genetic algorithms to change the environment up and then use the genetic algorithms to optimize your path, right? And then the top right image is from some research that I'm doing in Dr. Chin's lab. So that's the robot that we're using in the lab and the virtual twin. So here are my references. Thank you so much for listening to this presentation.